Hello, welcome to lecture 27 of the course. Last week we have studied and discussed about circuit quantum electrodynamics. This week we are going to study about cavity quantum optomechanics, which turns out to be a very big branch of quantum optics in recent times, and it has impacted other branches of physics as well. So let's begin. Cavity quantum optomechanics studies the interaction between light and mechanical objects using quantum optics tools. Optomechanics explores the interaction between electromagnetic radiation and nanomechanical or micromechanical motion. And as we will discuss in this lecture, it will be clear to you how this interaction takes place. Primarily, in short, optomechanics deals with coupling of light and mechanics. Quantum optomechanics is a very active area of research which aims to achieve quantum control of mechanical motion to mesoscopic and macroscopic system. Mostly, the researchers are focused on studying cavity optomechanical systems because, as you will see, such systems offer strong interaction between light and mechanical motion. A typical cavity optomechanical system consists of two mirrors, out of which one is fixed and another one is movable. These systems may be of micrometer or nanometer in dimensions overall. The electromagnetic radiation, generally a laser light, is incident on the system may get coupled to the movable mirror. This optomechanical coupling is the root of all phenomena such as quantum entanglement, and in this case quantum entanglement happen between photon and phonon. Photon is the, as you know, quanta of light, and phonon is the quanta of the mechanical motion. And then state transfer can also happen between photon and phonon or phonon and photon, and this is extremely important for various application, particularly in the so-called quantum transaction, and I think I will discuss it later on. And then squeezing of mechanical states or photon states. You have to note one thing, that this movable mirror can vibrate in the frequency range of kilohertz to gigahertz. And what is quite remarkable is that this model of two mirrors, one fixed and the other one is movable with light or radiation incident at one end, is capable of explaining a plethora of very different looking optomechanical system. For example, here in this figure, which I have taken from the journal Review of Modern Physics, is basically a review article on cavity optomechanics. Here you see these are very different looking system, and they have also mass is also different from gram to femtogram, again femtogram to zeptogram. That means that is I think 10 to the power minus 21 gram or so. That kind of variety of system can be captured by this simple looking model of two mirrors, out of which one is fixed and another one is movable. The main ideas of quantum optomechanics, however, were largely driven by the experimental search for gravitational waves in the 1970s and 1980s, particularly by the work of Vladimir Brzezinski, a Russian physicist, experimentalist. He was an experimentalist as well as a very good in theory as well. And you know, this finally resulted in the so-called recent LIGO, Laser Interferometer Gravitational Wave Observatory, and this LIGO resembles a cavity optomechanical system at a very large scale. LIGO antennas in fact operate by optically measuring the changes in the positions of large size test masses that serve as the end mirrors of large path length, which is generally on the order of kilometer long. And this is basically a Michelson interferometer. The gravitational waves produce time-dependent variations in the curvature of space-time, resulting in extremely small changes in the optical path length of the interferometer arms, and a modulation of optical transmission through it. Now, with the availability of advanced micro and nanomechanical devices, it is possible to realize such interferometric setup at a very small scale, and it opens the path to study quantum physics at macroscopic regime apart from numerous quantum technology applications, some of which we are going to discuss in this particular section, maybe in a different lecture. Now, at the core of cavity optomechanical system is the coupling of mechanics to light, and it happens through the so-called radiation pressure. And now we are going to understand what is radiation pressure or radiation pressure force is. To understand the concept of radiation pressure, consider this situation. Say we have a very thin mirror, and this mirror is perfectly reflecting. On this mirror, an electromagnetic radiation is getting incident vertically. Say a light wave is getting incident on it vertically. Now the question is, what is the momenta imparted to the mirror by this light, assuming that the mirror is not fixed, means it can move. Say it can move along this direction. Well, if you just consider a single photon, if I just consider a single photon, then you know the momentum the photon has is P is equal to h by lambda, or you can also write it as h bar k, where k is equal to 2 pi by lambda. Because the mirror is perfectly reflecting, the change in momentum of the photon after it's getting reflected is delta p is equal to, when it is getting incident, its momentum is h bar k, and when it is getting reflected, its momentum is minus h bar k. So therefore the change in momentum is going to be twice h bar k. Okay, so magnitude wise delta p is equal to twice h bar k, or 2h by lambda. Lambda is the wavelength of the photon. Now for a stream of photons, the force imparted by the mirror will be, let me write here, for a stream, earlier I just considered about one photon, but let me now consider a stream of photon. For a stream of photons, the force imparted on the mirror is going to be F is equal to, in time t, would be rate of change of momentum divided by the time, but that's because of a single photon, but it is a stream of photons, so let's say there are n number of photons are there. Okay, so n number of photons are there. Let me write here n photons. So this is the force that is getting imparted on the mirror, and if I write this way, delta p is equal to twice h cross or h bar k by t, and you know that k also I can write it as omega by c, so I can now write it as n photon twice h bar omega by ct. You know that h bar omega is the unit of energy, so basically you are having energy per unit time, that's give you the power. So from here you can easily make out that this is going to give you force is equal to 2 times power divided by c. Okay, c is the speed of light, so p is here power of the radiation. So this is a very important formula and well-known formula, and in fact this is basically the radiation pressure forces. So this is the radiation pressure force, and it has lot of utility in many branches of physics, particularly you may have heard about optical tweezer, which is basically it's basically play of the radiation pressure force. Now, as an example of radiation pressure force, the radiation pressure force due to sunlight, let me write here the radiation pressure force due to sunlight. Sunlight has wavelength on the order of, you can consider it to be around 400 nanometer, and it's calculated to be, the pressure force is calculated to be on the order of very tiny, on the order of 10 to the power minus 5 Newton. So as you can see, it's a extremely small force, and this is the reason why in general we don't feel this particular force if we stand on the sunlight, right? Now let me take the analysis a bit further. First, let me ask this question: how much displacement can happen if a single photon of wavelength say 10 to the power minus 6 meter, that means 1 micrometer, falls on a movable mirror of mass 1 nanogram, that means 10 to the power minus nanogram. So let's see if we can answer this question. To do that, let me consider, basically the situation is like this. We have a movable mirror like this movable mirror. Let me say this mirror is attached to a spring of spring constant say K, and the mass of the movable mirror is M, and a single photon is getting incident on the mirror. Okay, as we have already learned that the photon is going to impart momentum to the mirror, and the change in the momentum is delta P is equal to twice h per k, and that is equal to 2h by lambda. Now let's say, because the mirror is attached to the spring and the spring is assumed to be massless, okay, then the energy stored on the mirror, if the mirror is getting displaced by a distance of say delta x, let me say this mirror is getting displaced because of the impact of the photon, it is displaced by an amount delta x, then the energy stored in the mirror, energy stored in the mirror spring system, in the mirror spring system, it's from basic physics, it's very trivial to calculate. System is 1/2 k delta x square, right? That is the potential energy stored in the spring, and this also I can write it as 1/2 k is equal to m omega m square, where omega m is the resonance frequency of the mirror spring system. Okay, and you have here also delta x square. M is the mass of the mirror. Due to energy conservation, because the kinetic energy is getting imparted by the photon, so I can apply energy conservation. This kinetic energy is getting converted to the potential energy, so I must have 1/2 m omega m square delta x square is equal to delta p square divided by twice m. Alright, so this is what I have, and delta p is equal to twice h per k whole square divided by twice m. Okay, from here I can write delta x square, some algebra I have to do. Delta x square is equal to 4 h square k square divided by m square omega m square. Now at this stage, okay, let me also write here, because k is equal to 2 pi by lambda, so I can write it as 16 h bar square. I will have pi square, okay, divided by m square omega m square lambda square, where I have used the fact that k is equal to 2 pi by lambda. Now recall that there is this important quantity called the displacement due to 0 point fluctuation, which is a completely quantum mechanical quantity. This is given by, for a harmonic oscillator kind of situation, we have already discussed it, h bar divided by twice m omega m, right? This is what we have. So this means that x square 0 point fluctuation is equal to h bar divided by twice m omega m. Utilizing this, in this expression here, you can very easily get this expression, get this formula. Actually, please try to get it. You will get that you can show that delta x divided by this ratio of the displacement with respect to this displacement due to 0 point fluctuation is equal to 8 pi by lambda into x 0 point fluctuation. This is a very important relation, and please get it. Now if we are given that in our case the mass of the mirror is given, m is given to be 10 to the power minus 9 gram, okay, and lambda is 10 to the power minus 6 meter. If I put all these things in the formula, then you will get delta x, the ratio of the displacement of the mirror with respect to this 0 point fluctuation, x zpf, would turn out to be 10 to the power minus 6. Now as you can see from this expression that this displacement of the mirror is utterly negligible, okay, and very insignificant. In fact, to see quantum signature or quantum effect, the displacement have to be at least on the order of displacement due to the 0 point fluctuation. Okay, so this way, if you are just having only a single mirror and a photon is incident on it, this is not going to help the cause. That means you cannot have any significant displacement. Then what to do? Well, let us see if we add a cavity, if it helps. So what we can do, we have this spring mirror system is there. Now let us put a cavity. So we put this cavity, and now the photon is getting incident on it this way. Okay, now what is going to happen is that once this photon is entering into the cavity, inside the cavity it's going to make lot of round trips depending on a quantity called f, which is called finesse. Okay, this quantity is called finesse. This gives the number of oscillation of the photon inside the cavity. Now because of this, the momentum, that is the change in the momentum of the photon, is going to be finesse into delta p. Delta p is the usual change in momentum due to a single photon, as we have already discussed. Now it turns out that if the cavity lifetime is much smaller than the oscillation period, then it can be shown that delta x by x 0 point fluctuation is on the order of 2f by lambda into x 0 point fluctuation. And the finesse is it can be a very large quantity depending on the quality of the cavity, and generally it can be taken in such a way, if the cavity is a good one, then this ratio of the displacement of the spring mass system with respect to the displacement due to 0 point fluctuation is greater than 1, and this means that quantum signature or quantum effects can be now prominent. That means that there is going to be a significant displacement is there, and we can study quantum effects in such a very nano size system, and this is one of the major reason for extensive exploration of cavity optomechanics. So you see that a cavity optomechanical system can be represented by a set of two mirrors, out of which one is fixed and the other one is movable. In fact, this should remind you about the so-called Fabry-Perot cavity setup, where two mirrors are fixed, not movable. So let's say these are the two mirrors separated by a distance L, and understanding Fabry-Perot cavity helps a lot. I'm not going to discuss about it in details. You can consult any optics textbook for details. Here I'm just going to give you the some important facts about Fabry-Perot cavity. So here I'm going to give you some facts about Fabry-Perot cavity. So if a light or electromagnetic radiation, say light wave, is getting incident on it, on this Fabry-Perot cavity, then this light can enter into this cavity provided a certain condition is getting satisfied, and that condition is called the cavity resonance condition, and that condition is that k into 2l, k is the wave vector, into 2l means in one round trip, as you can see, it is going to cover a distance of 2l, because these mirrors are separated by distance l, so total distance is 2l, one round trip distance is 2l. That should be an integral multiple of 2 pi. This is the cavity resonance condition, where m is an integer, m can be 1, 2, 3 and so on. Okay, and this is called cavity resonance condition. This cavity resonance condition can be written in various different forms. For example, I can write it like this. Because of this condition, these wave numbers are now getting kind of discretized, m into pi by l. And also you know that k is equal to omega by c, and again omega is equal to 2 pi into nu, right? Omega is the angular frequency, nu is the frequency. So because of this, you can write the cavity resonance frequency, this cavity resonance condition in this form. Say omega m is equal to m into pi c by l. Then you can also write it as nu m is equal to integral multiple of c by 2l, where c is the speed of light. Or you can also write it as lambda m is equal to 2l divided by m. So all these are actually points to the same fact, but very useful forms. And also you see from this condition that only certain modes of frequency can enter into the Fabry-Perot cavity. Not all frequencies are allowed to enter into the cavity, and such frequencies whichever is entered, that enters into the cavity, that has to satisfy this resonance condition. And when this resonance condition is satisfied, the cavity is filled up with intensity, with high intensity, and this is typically expressed by the intensity versus frequency plot. So let me give you a typical plot. If you plot the intensity inside the cavity, Fabry-Perot cavity, versus the frequency, then you are going to get plot of this type. So you will get peaks like this at different frequencies, resonance frequencies. So you have here nu m, then you are having here nu m plus 1, here you are having it as nu m minus 1, and so on. Okay, and as you can see here, this peak is the intensity maxima, I max, and all this peak has a line, is a width, that is the full width at half maximum. So this full width at half maximum is extremely important, and that is denoted as delta nu fw hm. This quantity basically depends on the cavity lifetime, delta nu fw hm, I mean to say, and it depends on the cavity lifetime, means how long the photon can sustain its oscillation inside the cavity without getting lost. So it in turn is associated with the finesse of the cavity. In fact, you can consult any textbook, and that is what is important for us is that this particular expression delta nu FWHM is given by FSR divided by finesse F. In fact, rather than writing it just like this, finesse is denoted by this symbol, slightly, this kind of F, and FSR is the short notation for this is the short form for the term free spectral range. Free spectral range. And this free spectral range is nothing but it's the distance between two adjacent peaks. So the distance between the adjacent peaks, this distance, this is called FSR. So therefore, as you can see, FSR is simply equal to nu m minus nu m minus 1. Okay, so it is very easy to work it out. You have nu m is equal to m into c by 2l, and nu m minus 1 is m minus 1 into c by 2l. So therefore you are going to get simply it as c by 2l. So c by 2l is the FSR, or the free spectral range. Okay, now another important fact is that the photon lifetime or the cavity lifetime and this full width at half maximum are related to each other for a good Fabry-Pérot resonator. This is given by this cavity uncertainty relation. TP is the photon lifetime, and this full width at half maximum or the bandwidth delta nu FWHM is equal to 1 by 2 pi. So what it means that if you have a very sharp peak, if you see this plot here, intensity versus frequency plot, that means that your delta nu FWHM is very small, and which in turn it means, because of this uncertainty relation, that the lifetime of the photon is higher there. That means the photon can survive inside the cavity for a longer amount of time. Okay, so that's the importance of this cavity uncertainty relation. One very important quantity associated with a cavity resonator is the so-called quality factor, and by convention you know that this quality factor capital Q is defined as 2 pi times, which is the ratio between the energy stored inside the cavity divided by the energy loss per oscillation cycle. Okay, and for a cavity, Fabry-Pérot cavity, this quality factor is given by nu m, that is the cavity resonance frequency, divided by the full width at half maximum FWHM. So these are some important points you should keep in mind. And also you see that for a very good resonator, that means the resonator which can hold the photon inside it for a long amount of time must have a very high Q, or quality factor. In fact, quality factor and finesse are related to each other, and it can be very trivially shown that this quality factor and finesse are related by this expression. In a Fabry-Pérot cavity, it is m into finesse. M is an integer. Quality factor is an integral multiple of the finesse. Now, having all these backgrounds at our disposal, let us consider our model cavity optomechanical system, and at first let us guess the Hamiltonian of the system. As you can see, the whole system has three primary components: the laser, which is driving the optical cavity, the cavity mode, and the movable mirror and its interaction with the cavity mode. The Hamiltonian therefore consists of the following parts. So H is the Hamiltonian of the whole system. So it has parts, say HO refers to the optical mode that is inside the cavity, optical mode. Then the mechanical mode, let me denote it as HM. So this refers to the mechanical mode. And then there is interaction between the optical mode and the mechanical mode. Therefore, there is a term HOM for describing that interaction. And then we have this laser drive. Apart from that, there are some other terms are also there, but which we will not talk about here at this moment. Now the optical mode behaves like a harmonic oscillator, as we already know about it. So we can immediately write, in fact, a better diagram to represent the whole thing is this, because this optical cavity or the optical mode is going to be represented by this annihilation operator A. So this HO is going to be given by H bar omega optical, that is the frequency of the optical mode, A dagger A. Okay. However, because we now have a movable mirror, the cavity mode frequency, that means omega optical, this frequency is now a function of position. So it's now a function of position, right? So therefore, let me just write it separately and explain it. This function omega optical, this cavity resonance frequency, is a function of x, because if I consider a fixed mirror, for example, for that we have omega optical, this frequency, as we have discussed, as I have told you about the Fabry-Perot cavity, that only those frequencies can enter into the cavity which satisfy this particular condition. It should be integral multiple of pi c by length of the cavity, pi c by L. And now because this movable mirror can get displaced by small amounts, say x, so therefore this is, I can write it as n pi c by L plus x. In fact, if distance is very small, I can express omega optical as a function of x in this form, n pi c L. If I take in the denominator common, then I have 1 plus x by L. X by L is very small compared to 1 unity, so therefore I can write omega optical as a function of x as n pi c by L. It is nearly equal to, not exactly, nearly, I can approximate it as 1 minus x by L. Okay, so this is going to be my frequency of the cavity, optical cavity mode. So now also you see this quantity is the original our omega optical. So let me write it omega optical. Then I have 1 minus x by L. Now putting this in the Hamiltonian, so I have H is equal to, I have H bar omega optical 1 minus x by L into A dagger A. Now here I have two parts. Now because I am doing things quantum mechanically, so x is a position operator, so let me write it that, and as you can see that is coming into this scenario now because of the movement of the mechanical mirror. So I have now two terms out of it, omega optical A dagger A. This describes the energy of the optical mode, and this second term H omega optical divided by L into x cap A dagger A. This basically gives the interaction between, this is the interaction between the optical mode and the mechanical mode. Interaction between optical and mechanical mode. Optical and mechanical mode. From the mechanical mode, this position operator is coming, and this mechanical mode is actually the movement of the movable mirror is happening like a simple harmonic oscillator, and a typical frequency of this mirror, movable mirror, is in the range of kilohertz to megahertz. On the other hand, this is optical frequency oscillates at the terahertz regime, right? Optical frequency regime. So there's a big difference in frequencies are there. So that's why the quanta of the mechanical mode is said to be phonon. Okay, so therefore what we have already out of the total Hamiltonian. Now we have all the other terms are also there in the Hamiltonian. Here the first term refers to HO. Now let me, and this term refers to HOM, optomechanical interaction. What about the mechanical mode? Because the mechanical mode is also a harmonic oscillator, so we can write it as H cross omega m. Omega m is the oscillation frequency of the mechanical mode. We are assuming that only one mode of the mechanical oscillator is getting excited, so therefore we are writing it in this form. So this is the Hamiltonian describing the mechanical mode, and writing incorporating this, therefore we have the total Hamiltonian. Now we have these terms: h bar omega optical a dagger a, that is the optical energy, cavity mode energy. Then we have h cross omega m b dagger b, and we have this interaction term, that is h bar omega optical by l x cap a dagger a. And then we have this laser drive is also there. I will come to that in a minute, but before I go to that, let me write this position operator of the mechanical oscillator as b plus b dagger into the 0 point displacement due to the 0 point fluctuation, where 0 point fluctuation, displacement due to 0 point fluctuation, is defined as h bar divided by twice m omega m under root, where m is the mass of the movable mirror. Okay, so with this, and also by the way, let me define this quantity called z, a parameter z, which is h optical by l. And if I do that, then I have my Hamiltonian as h is equal to h bar omega optical a dagger a, okay, plus h bar omega capital omega m b dagger b. Then I have minus h bar z x 0 point fluctuation, right? Then I have b plus b dagger dagger a plus the laser drive. We have this. I can actually make it a little bit more simpler if I defined a quantity called z, defined as small z into this 0 point fluctuation, and this parameter capital Z is called defined as optomechanical coupling parameter. This is called optomechanical coupling parameter. In terms of this optomechanical coupling parameter, I can write my Hamiltonian H as h bar omega, rather than omega optical, let me now onwards write simply h cross omega 0 or omega o. Then I have a dagger a, okay, plus h cross capital omega m b dagger b minus h cross capital Z b plus b dagger a, okay, plus h the laser drive. So let me write laser drive. So with these things, now let me talk about what is this laser drive. You see, the laser drive, it is easy to write because what is happening is that this external laser drive is creating a, as you can see in this diagram, this external laser drive is creating a optical mode inside the cavity, and it exists inside the cavity as permitted by the cavity lifetime or the cavity decay rate. This cavity decay rate is say kappa. Okay, and also it is related to the quality factor of the cavity, because you remember quality factor decides how long the this or the finesse, how long this cavity mode is going to oscillate inside the cavity, and that is equal to omega 0, that is the resonance frequency of the cavity, or omega opt, but now I am denoting it as omega O or omega 0 by kappa. Kappa is the cavity decay rate. Okay, so now let me write the H drive, this laser drive part of the Hamiltonian. So this I can now write it as IH bar omega, capital Omega drive. A laser is getting created, a laser photon is getting created, cavity photon is getting created inside the cavity, and the laser frequency is say L, omega L T, and this Hermitian conjugate would be A e to the power I omega L T. So this is what the drive is, where this magnitude of the drive is given by this expression kappa, that is the cavity decay rate, and this is the laser input power P in H cross H bar omega L. Omega L is the laser frequency. So let me write all these terms here. Kappa is the cavity decay rate, all right, and P in is the laser input power, and omega L is the laser frequency. So with this I have my full Hamiltonian now. H is equal to H bar omega 0 A dagger A plus H bar capital omega M B dagger B minus H bar Z B plus B dagger into A dagger A plus I H bar omega drive A dagger e to the power minus I omega LT minus A e to the power I omega LT. Now you see, you can easily get rid of this explicit time dependence by going over to a rotating frame of reference, and we have done that earlier when we have discussed two-level atomic system, two-level atoms. So going over to a rotating frame, and thereby I take this unitary transformation, say u is equal to e to the power minus I omega L A dagger A T, then you can easily show, you can get this expression, this Hamiltonian. H is equal to minus H per delta, delta is the detuning parameter, A dagger A plus H cross omega M B dagger B, okay, minus H per Z B plus B dagger A dagger A plus I H per omega drive A dagger minus A, and here this detuning parameter delta is omega O or omega 0 minus omega L. So this is the final Hamiltonian that we have got, and we are going to discuss it in great details in the next class. By the way, in a real situation, the optomechanical system interacts with the surrounding or the environment as well, and these effects also needs to be taken into account, and we will do that in the next class. Let me stop here for today. In this lecture, I have briefly introduced you to the area of cavity quantum optomechanics. We have written down the optomechanical Hamiltonian describing the cavity optomechanical system. In the next lecture, we are going to study this cavity optomechanical Hamiltonian in somewhat great details. So see you in the next lecture. Thank you so much.